All right. I believe yesterday we were working on page 455, and we started yesterday to look at how we can calculate the volume of a 3D object when we're given, or we can figure out, the area of a two-dimensional object. Okay, and we looked at some YouTube videos that kind of showed the rotation to help us visualize how we can go from a 2D area to a 3D volume. And depending if the area always touches the axis that we're revolving around, or if it doesn't, we're either creating a disk, aka a solid figure, or a washer, something that has a missing chunk in it in some way. So on page 455, we were looking at this parabola in linear area, and we're trying to revolve it around different places or different lines. You just need to refresh me. Did we finish the top left box? Yeah, we got like 60 something for the area. Is that right? Or what was our area for the 45? I'm sorry. I kind of just gave away the next answer, I think. So so let's try the bottom, or the next one down below. Okay. So taking a look at the area, we want to revolve that area around the line y equals 4. So let's go ahead and draw that in, just so we can see what's going on. All right, we're taking the same area section, but this time we're going to revolve it around y equals 4, okay, not the x-axis. If we were to draw in some rectangles, do those rectangles touch the axis we are revolving around? No. We have all of this white space in there. Okay, so this is another example of a washer. If we were to revolve the area, we would have some type of cone shape, almost like a bowl. You can think about it that way. So let's see if we can set up our volume integral, and then we'll go ahead and use our calculator to help us from there. In order for us to calculate volume, we have to integrate area. And since we're going in a circle, we're going to utilize the area of a circle, which is pi r squared. Now the r, that radius, we got to calculate. So we got to calculate the radii, which is basically the rectangles that you're drawing in. Now for a washer, I put the formula up on the board just so we can reference it and we don't have to kind of flip our notes. We need to figure out what is the outer function, aka the function that is furthest away from that axis of rotation. So between the line and the parabola, which one is the furthest away? Are we thinking the parabola? Okay, so that'll be our outer function. And we need to subtract the axis that we are revolving around. Now, up to this point, we were either revolving around the x-axis or y-axis, which have values of 0. But in this case, we're revolving around the line y equals 4. So we're going to have to subtract 4. We now have to subtract the inner radius, which is basically representing this white section. We're going to subtract that volume, that way it goes away because it's white empty space. The inner function is the one closest to the axis we are revolving around, so that would be this line, x plus 2. And again, we have to subtract the axis we are revolving around, which would be 4. So from there, it's just going to be some calculator work. Oh, we forgot the bounds. Beginning point, ending point looks like -1 to 2. Can we do some calculator work from there to get our volume? Do you get Liam? Go ahead.
67.858.
858. Can we confirm? Is it? I'll put a battery in it. Thank you. All right, so there's one thing I kind of want to just go over briefly with this answer. When we revolved it around the x-axis yesterday, we got 45-ish as our volume, but we're taking the same exact area. This time we're revolving it around a different line, and notice how it's 67.854. So why do you think the axis of rotation matters? We're taking the same area, but we're changing where it's rotated. Can we kind of think about why that axis is important? What do you think? Yeah. It's the amount, exactly, the amount of open space. Now, in previous one, if we were to revolve it around the x-axis, we just had this empty space, but that's a completely different amount than this empty space. So you're creating a different three-dimensional object depending on how you rotate it. For example, let's say that I'll use my pinky as an axis of rotation. If I put my other hand close to that axis and revolve it, notice how that's just going to create a small shape. But if I let the area be further away, okay, aka like a different axis of rotation, and I revolve it, I'm going to be creating a bigger shape. You see the difference? So it's still the same area, it's still my hand, but depending on where it's located in terms of that axis, you're going to be creating a different solid, therefore a different volume. Okay, so even though it's the same area, the axis of rotation does matter. It's important to make note of that. Let's try the next one. So we'll erase what's going on here. We're going to revolve around y equals -2. Let's draw in some rectangles. Do those rectangles touch our axis of rotation? No, so we got another washer. That means we need to take into consideration that outer function and inner function, because that white space is going to be empty when we revolve it. So let's put the pi out front. That's from the area of a circle, pi r squared. Our bounds are still the same because we're working with the same area. And let's think about the outer function first. So in relation to this axis that we are revolving around, the outer or furthest away function would be the line. So we have x squared plus 2. And then we have to subtract the axis of rotation. So if we need to subtract -2, that's going to go ahead and change to a plus. Yep. Oh, thank you. Too many 2's. All right, let's go ahead and try to figure out the inner radius. So that would be the closer function to the axis, which would be the parabola. And then we have to subtract the axis we are revolving around. So again, subtracting -2 would change to a plus. And we'll calculate our volume on our calculator from there. Did you get it? Yeah.
101.78.
0.7 what?
88.
88. Can we confirm? Did someone else do it that quick as well? You got it? Perfect. All right. Let's go ahead and try some other ones on the back. We're going to switch it up a bit. So, notice how it's a very similar shape. We still kind of have a parabola type function and a line, but now we're going to take a look at how we can revolve it differently, maybe around the y-axis. So this is going to bring in a y area. We're going to have to use y variables to help us out. Let's try the first one. find the volume when the region is rotated about the y-axis. So we'll kind of draw in our little arrow there. That's what we're revolving around. Since we're revolving around the y-axis, our rectangles should go horizontally. Do those rectangles touch the axis of rotation every single time? Nope. So we have another washer. And let's check out our volume. All right, so pi times our integral. If we're revolving around the y-axis and using our horizontal rectangles, we have to make sure every other part of this integral involves the variable y in some capacity. So in terms of your bounds, they should be going from the y-axis now. So that looks like -1 to 2. And since we have a washer, we still need to figure out the outer radius and subtract the inner radius. So in relation to this y-axis, the furthest function away is the line, but we can't write in x minus 2 because this is a y-axis area. We're measuring it to the y-axis. Can we somehow change this around so it has a y variable in the function? Yeah, y plus 2. We can add the 2 over. So the outer radius or function is y plus 2. And then we have to subtract the axis we are revolving around. If that's the y-axis, that simply has a value of 0. Let's do the inner function. So the closer function to the axis is that parabola type shape. They're telling us it's plus or minus the square root of x. But if we want to solve for x like we did in the previous example, we just square both sides to get y squared. So the inner function's y squared minus 0, the axis we're revolving around. We'll go ahead and calculate our volume. It's y's on your paper, but you can type in x's on your calculator. Yeah?
Would it be 45.239?
Yep. Does that value look familiar? Where have we seen that before? The one from yesterday, right. So I know we don't have the work on here, but notice how from yesterday it was 45.239. And this one was when we were revolving around the x-axis. Take a look at the description, or at least the picture. Notice how here you have that area shape and it's touching your axis of rotation at some spot. If you flip it, you have the same area touching the axis at the same spot. So it's going to produce the same volume, it's just that your object is oriented differently. Instead of being kind of vertical like the previous one was, this one, if you revolve it, is going to be horizontal. So it's still the same object. It's whether you want it to look horizontally or vertically. Okay, it's still the same object, so it's going to have the same volume, which is great. All right, let's try the next one. Find the volume when the region is rotated about the line x equals 4. So I'm going to go ahead and erase the y-axis because now we're going to revolve it around the x equals 4 line. Clearly those horizontal rectangles are not touching the axis at every single spot, so this is going to be another washer. Let's go ahead and set up our volume. Okay, we need pi r squared or some variation of that. So the pi's out front, bounds on the y-axis, -1 to 2. The outer function in relation to this new axis of revolution or rotation is the curve, and we said that was y squared. And now we have to subtract the axis that we are revolving around, which has that x value of 4. Let's do the same thing, but now for the inner function. So in relation to our axis of rotation, the inner or closer function is the line. We said that was y plus 2. And then subtract the axis, which was 4. Go ahead and let the calculator do the work from there. Did you get it, Daniel?
67.858.
0.858. All right. I think that's the same area we did on the previous example. If you were to switch back, you would have the same area value touching your axis of rotation at kind of that top corner. So again, it's the same shape because it's the same area being revolved around the same line. It's just oriented differently, whether you want it vertically or horizontally. So those two are kind of good ones to check our work. Let's try the last one. So we have x equals 7. That's somewhere off of our paper, but we can still imagine drawing that line in it if we wanted to. All right, clearly the horizontal rectangles are not touching that axis, so we have another washer. Our bounds are still -1 to 2. So in relation to this new axis, the outer function or furthest away function is the curve. That was y squared. And then subtract the axis we are revolving around, which is that value of 7. Okay, so we have pi r squared. That's the volume from the outer function. We now have to subtract the volume from the inner function, which the closer one would be the line, minus the axis of rotation. Anybody get it? Good, Daniel?
152.681. 152.
That's close. I got 153.3 something. So we're in the 150s. Let's see. You know what? I'll take yours. 152.681. Sounds good. Can we confirm? Perfect. All right. How are we doing with volume? Doing okay? We have two different methods, disc versus washer, and it all depends whether your rectangles touch the axis of rotation at every single spot or they don't. Okay? That's basically it for this section. So we'll stop there, but we still have a solid like 15 minutes or so. So I would totally take advantage of that to try some homework problems. That way we can enjoy our break and not have to worry about anything over break.